So from our previous examples, we had been defining the derivative of f at some point xi equal to the difference between the following point and the current point divided by our step size plus some remaining error term. This can be rewritten as the derivative being equal to some change in f at point I divided by h plus our error term of order h. Now this is known as the first forward difference, and we know that h is our step size, and another way of thinking about this is the length of the interval over which our approximation is made. So why is this called the first forward difference? And well, it really comes in from the fact that we are looking at the next step, in other words, I plus 1. So we can illustrate that with a graph. If we have some function that has a particular shape, and we are interested in the derivative at this point I, we are calculating this derivative based on this point at I plus 1. So in other words, we are shooting forward, hence the name forward difference. Okay, but this is one of many ways that we can approximate our derivative. And we can see now how the Taylor series is becoming useful to explain to us how we approximate the derivatives in numerical methods. So the Taylor series can be used to approximate the derivative from a backward difference approximation as well as a centered difference approximation. Okay, so if we look at what a backward difference approximation is, well, we can do that from, again, looking at a graph. So if we plot some function, and we are interested in the derivative at this point I, we can calculate this derivative based on the preceding point. In other words, I minus 1, this point. Again, you can see how we are shooting backwards to figure out our derivative. Okay, this can be written as, well, if we do the Taylor approximation, so to calculate the value at f of xi minus 1, so f of x at I minus 1 is equal to the value of f at xi minus the first derivative at xi multiplied by h plus the second derivative xi h over 2 factorial. Okay, so we can approximate our derivative of f prime xi approximately equal to f of xi minus f of xi minus 1, again because we're shooting backwards, divided by h. And this can be rewritten as our upside down triangle, f at point I, h. And this is what we term the first backward approximation of the derivative. But now there's another way that we can do this, calculate or approximate the value of the derivative, and that's by using a centered approach. And in order to do that, we subtract the backward difference from the forward difference. And why do we do that? Well, let's just take a look again at our plot. We had our function, and we wanted to calculate the value of the derivative at point I. And initially we had used the forward approximation, so that is I plus 1. And I had just shown you how we can use the backward method. So that is I minus 1. Okay, so if we take the difference between these 2 points, we are approximating the derivative about point I. So that is why we subtract the Taylor series approximation at I minus 1 from I plus 1. So that is to say that and I encourage you to do this for yourself, the Taylor series approximation, f at x of I plus 1 is equal to the value of the function x I minus 1 plus twice the value of the derivative at x of I multiplied by our step size. And what you'll notice is that the second order terms vanish and we are left with third order term, f to the power of 3 with third derivative xi h cubed divided by 3 factorial. Okay, now we can rearrange this again to look at the approximation of the first derivative. That is f of x prime is equal to the value of f at xi plus 1 minus the value at x at I minus 1 divided by twice our step size minus f to the third derivative at xi h squared over 6. Notice now that our error term scales with h squared. So in other words, it's of order h squared. And this is very important because now we can see how the Taylor series has helped us show that the centered difference approximation of the first derivative gives us a much more accurate approximation. So let's look at this more in detail in the next example.